Okay, toxic release and dispersion model, video 3. Okay, as a recap, we already discussed about what you need for your toxic release and dispersion model. The requirement, first you need to identify your design basis. Then second one, you need to develop a source model. And the third one, you need to use a dispersion model. So, in your dispersion model, you have two different models, which is based on your dispersion characteristic. Is either Puff model or Plum model. Okay, we will already look what is the equation that will involve in our dispersion model, where it also include this eddy diffusivity coefficient. Okay. Next one, we will look further what is their 15 cases. Okay, 15 different cases that involve the Puff and Plum models, and what is their correlated equation. Okay, so for eddy diffusivity, Kj, we assume it is a constant, so it involves 10 cases where Kj is a constant, eddy diffusivity is a constant. So, as a recap also, for vapor cloud behavior, there are 3 different cases, which is neutrally buoyant gas, positively buoyant gas, and also negatively or dense buoyant gas. Okay. Then there are parameters that involve in our gas dispersion, which is related to the duration of gas release. Okay. So the duration of gas release is either instantaneous, we call it a puff. When continuous release, we call it a plums, and also time varying continue. In previous video, I already discussed and already explained what types of parameters that affecting atmospheric dispersion model. Okay, the first one is wind speed, atmospheric stability, ground conditions, height of the release above ground level, HR, and also the momentum and buoyancy of initial material release. Okay, this is the stability classes. Okay, there are different stability classes for neutral, stable, and also unstable. So for a release which is categorized as unstable, okay, we use the stability classes A and B. Okay, then we also have a stable classes. Okay, stable stability classes in a class of EF. Okay, we also have neutral stability classes in class D. Okay, all these classes will determine what kind of equation that you will use, or what kind of coefficient that you will use inside your gas dispersion model. Okay, this is the figure relate to the atmospheric stability. Then we have a surface roughness. Okay, is it highly urban, residential area, cultivated land, flat land, open air, open water, and so on. Okay, so this terrain classification will determine what is your value for your surface roughness. Okay, Z note. Okay, this is your surface roughness value. Okay, for example, highly urban, we will use surface roughness ranging from 3 until 10. It depends on the density or density of this area. Is it many tall buildings? Okay, how many skyscrapers there, and so on. Okay, so highly urban, basically it is a center of cities with tall buildings, very hilly or mountainous area. Okay, then we also have an urban area, mostly in village and fairly level wooded country. Okay, so the roughness is lower as compared to the highly urban. As you can see, going down this terrain classification, you can see that the surface roughness is usually getting lesser. Okay, from large refineries, then small refineries, cultivated land, until when you see the terrain classification of open water and sea, their surface roughness already nearly to 0, 0.001 and also 0.001. So there is, when the surface roughness is nearly 0, it means that there is no obstacle or obstruction to the flow or to the direction of the gas, okay, the gas dispersion. Okay, there is no obstruction of the gas dispersion. That's why the surface roughness is nearly 0 as compared to highly urban and urban area. Alright. Okay, so neutral and positive buoyant Plum and Puff model. Back to basic equation. This is our basic equation. We will look how we can derive, okay, this basic equation into the one that will relate to the Plum and Puff model. Okay, so this is for Plum model, how the equation for the average concentration can be explained. Okay, this is just for your information. Okay, this is the basic of a Plum model. Okay, the basic equation for Plum model, and this is the basic equation for the Puff model. Alright, we just look into case by case, okay, where how the situation or the condition at that case will transform this basic equation into simplified equation. Alright, because most of these cases, okay, case 1 until case 15 actually just depend on this basic equation. Okay, only when the situation or the condition at that time will determine or will make this derivation getting easier. Alright, so this is case 1 where a steady state continuous point release with no wind. Okay, so there is no wind involved, only a steady state continuous point release. So the applicable condition are constant mass release rate. Okay, QM is constant. There is no wind, meaning that our velocity or wind velocity is 0. We have a steady state, so the concentration and are constant, and eddy diffusivity also treated as a constant. So we simplify the equation and we got the analytical solution. Okay, the analytical solution is to be used to find the value of any parameters that you intend to determine. Okay, for example, for this analytical solution, you try to determine what is the concentration, okay, of the gas release at coordinate x, y, z. Okay, this is the concentration at this coordinate. So the equation is equal to Qm over 4 pi k, okay, eddy diffusivity, times roots of x squared plus y squared plus z squared. Okay, so to find out, if you want to determine what is the concentration, okay, at the location, you need to have the location. You need to have the information of the location, the QM, the constant mass release rate, and also the eddy diffusivity. Okay, so you can determine what is the concentration at that point. Okay, this is case 1. We will look further what is the relation between case 2. Okay, this case 2 is a puff with no wind. So the applicable condition are related to the puff release, instantaneous release of a fixed mass of material QM. Okay, QM star. No wind. Okay, still no wind, just like the case 1, no wind. So the velocity of wind is 0 and constant eddy diffusivity kj is equal to k star in all direction. So we try to simplify the equation, and this is the equation that can be simplified, where you can use it to find the concentration, okay, at point x, y, z, and at the time t. Okay, this time you have at the time t, x, y, z, t. So this is the equation. Okay, just if you look back, the information that you need to know for this case is basically same like the first case. Okay, you need to know the eddy diffusivity, your constant release rate, and also your coordinate. But you also need to know what is your time. Alright, in the next video, I will show you what is the derivation for case 3 until case 10.